Hi, this lesson is about solving systems of linear equations through elimination with modification. We should already know that a system of linear equations is just more than one linear equation. When we look at it graphically, we can see the point of intersection is the solution, but we are often asked to solve algebraically, and one way that we can solve algebraically is through elimination. Yesterday, video about how to solve using elimination in examples that looked like this. What's important to note is that we've had so far only examples where there are already additive inverses. This is a really important definition, so even if you've had it in your notes before, please include it again. Additive inverses are the same number with a different sign, and one example that we see is 2x and negative 2x. These are perfectly lined up equations, which is why it's a good candidate for this method called elimination. So 2x and negative 2x, like all additive inverses, like negative 3 and positive 3, cancel out. They give us a 0. But right next to it we have negative 5 and positive 3, both with the y term, and these are not additive inverses. We can combine them and we get negative 2y. On the other side here we have 11 and negative 9, and when we combine those we'll get positive 2. This should be familiar from last night's video. If it's not, please go back to that video now and then come back to this one. So to solve this mini equation, we divide by negative 2 on both sides and we get y equals negative 1. But since this is a system, we know that its solution is going to have an x and a y value. So we have to go back to one of our original equations. I'm just going to choose this one for now and substitute that value in for y, bringing everything else down. And now we have another equation that has just one variable, and we can solve this one for x. Again, this should all be familiar from last night's video. Alright, and let's undo that real quick. And when we divide by 2 on both sides, we end up with x equals 3 as our x value. So our final answer, the ordered pair for this system, is 3, negative 1. It's a really good habit to get into to check your answers by substituting. So please go ahead and do that on your paper right now. Then press play to check. Alright, so now we can see that by substituting our solution, which was here, into each equation, we took that first equation and I copied it down there. We got a true statement in the end, so we know that it's true for at least one equation, but we have to check in both. We took a look at the second equation and I wrote that down here. Again, we got a true statement. So since this solution satisfies both equations, it is correct. We can be 100% sure when we have these types of questions that we can walk away from it positive that we got the right answer. Now, today's example is a little different, and I want you first to take a look at this question. And in your notebook, please write down how the system is different from the previous example and all the examples you saw yesterday. What I hope you noticed is that there's no additive inverse. And that was a critical component of being able to use elimination. So if we want to solve algebraically, we're going to need to create additive inverses. Recall that additive inverses are the same number with a different sign. So when we ask ourselves which variable will we eliminate, we might check first and see the coefficient on both of these x terms is 1. So we're already halfway. We have the same number, we just need to do something to make it a different sign. So 1, its additive inverse is negative 1. You might ask yourself, what could we do to what could we do to positive 1 to get negative 1? So one thing we can do is multiply by -1, and we can do that to either equation. We just want to make sure when we do that to every term in each equation. So I'm going to do that to this bottom equation. It doesn't matter which equation we use here. -1x minus 8y and -3 is our resulting equation. Now the top equation we didn't change at all. 1x plus 3y equals -2. And we, again, wanted to get additive inverses. That was our goal, and we now have them. We have positive 1x and negative 1x. Since those are additive inverses, they'll cancel out, and we can solve like normal from here. Please pause and do that now. The new step is just creating these additive inverses, and if that part was confusing, please write down any questions you might have or rewind to listen again. So using the same steps we did yesterday, we should find the solution -5, 1. If you didn't, please look back at the notes here to check your work. We're going to move on to one more example. In the last example, we chose to eliminate the x value, but Troy and Gina are looking at this system of equations, and Troy says he wants to eliminate the x variable. Gabriella says she wants to eliminate the y variable, and our job is to find out if they'll get the same answer. We have to show work to justify. So if we want to eliminate the x variable here, we look for the x coefficients, 9 and -3, and I'm thinking about the multiples of 3, 3, 6, 9, 12, and so on, and the multiples of 9, 9, 18, and so on. And there's one that's in common pretty early on, 9 and 9. So I think I can make this 3 down here become a 9. If I multiply -3 by 3, that gives me -9, which is helpful because that is the additive inverse of the 9 we had up front. So I'm going to erase some of this so we have some room to work. Again, our goal is to make additive inverses, so we're going to multiply the bottom equation by 3, and we're going to multiply each term by 3. Go ahead and do this on your own and then press play to check. Make sure that you've distributed to each term in the equation. Don't forget about that 14. We multiply that as well. And the top equation we haven't changed, so that's going to stay the same. But now our two equations do contain additive inverses, and we can eliminate them. From here, it should be a familiar process at this point, so you can press pause and press play to check. I may have made a typo. I'm going to go back. So using those steps, we find the answer 2, 5, which was Troy's answer by eliminating the x variable. Let's go over now to Gabriella and see what happens if she eliminates the y value. So the y values, or the y coefficients right now, are 2 and 4. Again, I'm thinking about the multiples of 2 and 4. These ones might be kind of obvious to you now, but if there were more difficult numbers, we want to have a strategy that would work every time. So we have a common multiple, which is 4. We know that if we multiply 2 by something, we could maybe make this 2 into a -4, and what we'd have to multiply by is -2. Be very aware of these positive and negative signs. Remember, additive inverses have to have not just the same number, but also a different sign. So multiply this entire top equation by -2. And don't forget to distribute even to the other side of the equal sign. And we didn't have to change our bottom equation in this example. There may be times where we have to modify both equations. in a case where there's no common multiple, one thing you can always do is what I call switching up the coefficients. For example, if we had switched and multiplied this by 4 and this by 2, we'd definitely get the same answer. We just have to be careful of the signs. But since that's not the case here, let's continue like normal. Since we now have additive inverses, we can solve like we did yesterday. Pause. I'm going to ask that you pause and try this on your own, then press play to check. We want to see this in your notes. One quick thing that I'll point out, I think when I wrote this over here, I might not have had my negative sign very clear. Be sure that you're distributing -2 to each term. That can throw off your answer, so please be aware. I made that mistake here. I hope you didn't as well. So after solving for x, then using that solution to go back and solve for y, we got the 0.25, which if you look back at what we had from Troy, is the exact same answer. No matter which variable we eliminate, we're going to get the same answer. Because think about it, these equations are lines, and on the coordinate plane, it doesn't matter which one we're eliminating or modifying, they're going to have the same point of intersection. So that's it for tonight's lesson. Keep in mind the big ideas. Okay, the big idea tonight was about creating additive inverses. And to create additive inverses, we can make a list of multiples and ask ourselves, what can we multiply by to make additive inverses? We need equations to be perfectly lined up, x's over x's, y's over y's, etc., and to have those additive inverses in order to use elimination to solve a system of equations algebraically. This was the big idea from tonight's lesson. If you have any questions about it, please write them down or email us right away. Your teacher's contact information can be found on our class website on the left-hand column under the link that says Contact. We look forward to hearing from you and look forward to seeing you tomorrow in class.